So last class we talked about the WKB approximation, and if you remember, the WKB approximation was used for solving time-independent Schrodinger equations with a semi-constant v. Okay, so that's the main assumption we're making, that v was almost constant. Now today we're going to be talking about something similar. We're going to be putting the WKB approximation to the test in something called tunneling. I'm sure you guys have heard of it. And so far, what have we been doing? We've been assuming we're in this classical region where E is greater than V. Right? So this is the classical region. And what's happening in our classical region? Well, our P that we discovered, that's classical as well, so that's real. So we have a real P, E is greater than V, and we call this classical. So now let's extend this idea. Let's extend this idea to a non-classical region. So what do I mean by a non-classical region? Is, well, for this case, our classical region was where E was greater than V. Well, so now our non-classical region, E, is going to be less than V. And we also have something where P is no longer real. It's actually imaginary. It's not purely imaginary, sorry. So it's a complex number, but we know that because P before was in the real numbers, now we have P in the complex numbers. So how does that change our psi? So before, we had psi is approximately equal to 1 over square root, oh pardon, it's 1, a constant. So P of x times E to the plus or minus 1 over h bar, I believe, sorry, it's I over h bar. P of x dx. So that's what we had originally. But now, what we're doing here is we're now going to assume a new psi, and how that new psi has changed is that P's now a complex number. So we can't just pick square root of it, we have to say C square root of the magnitude of P. Right? And this kind of follows similarly for our exponential here. We have this plus or minus 1 over h bar, the integration of the magnitude of P dx. So again, it doesn't change much, but there are some noticeable changes to what's going on with P. And this is what we will use for the rest of for anything in a non-classical region. So we're going to use this wave function. That's what we call the WKB approximation. So let's just erase this stuff because I need this board space. But you guys should remember that because we're going to use it later. And I'll refer to it. Okay. So now consider a scattering problem of a rectangular barrier. So normally, normally we have this, here's 0, and before we have this wave function. So we have this potential barrier, right? We have this potential barrier here, and we have a wave function with E less than that potential barrier. So we have a waveform out here. in the middle here, well, in reality, what we're going to use is now, let's assume not that this is a straight barrier, but let's assume that this barrier has just a bunch of bumps, some bumps in it. Some lumps and bumps, some weird looks. Like normally, we know the solution to this square potential barrier, but now we're giving it some lumps and bumps, and what happens? Well, we assume that in here we have some dampening, right? We have this exponential dampening. And once we can sometimes transmit through that, if you guys remember. From when we solved that previously, we can transmit it with some low amplitude wave out here. This is, again, still our psi from before, but what's happening is it's just being transmitted through here. So now, let's break this up into 3 regions. We have region 1, region 2, region 3. And we can consider what happens in all 3 regions, okay? So in our first region, region 1, we can solve that, right? We know what happens if we have no potential. We can write an equation for that. So we can say that for x is less than 0, we have a wave function that kind of looks like this. It's going to look like our exponential that we referred to way, way back in the first class, right? It's going to look like some linear combination of these exponential, these complex exponentials. So a e to the I k x plus b e to minus I k x. Right? It's a linear combination of those complex exponentials that we said earlier, and also, since there's no v out there, v is 0, we can say that k is equal to square root 2mE over h bar. Sorry if you guys can't see that very well, but really, it's something that we've gone over before, so I didn't feel like it was necessary to write it very large. But we can also consider, so we'll call this point A, just for future reference. So the second region, we'll scrap that region actually. Let's not worry about the second region right now, because that's what we're going to get to. But in the third region, region 3, what do we have happening? So x is now greater than a. And where x is greater than a, we have another complex exponential, right? We have to have a complex exponential. It's the same thing we have over here. And over here, there's nothing really different between these two sides. It's just that maybe something changed in the middle there. So we have this, but we know that, for instance, it can't come back on itself, right? So if it traveled and got past this barrier, it's always going to be moving one way, to the right. So that means we'll always have this plus side, but we won't have a minus side. So let me just draw this out for you. So we have A, the amplitude going that way, and then some of it might be reflected, right? So that's our B, traveling that way. And then we have this, we'll call this F. F traveling that way, okay? So now, let's see what we have. So we have psi equal to F e to the I k x. Right, we only have that positive side because we're only going one direction. And if you remember, we also backed out when we were doing this question before, we also backed out something called a transmission coefficient. So that transmission coefficient, if you remember it, is what we call T, right? This transmission coefficient. It's of the form T equals F over A. So the magnitude of F over A, and they're both squared. So that is our form for this transmission coefficient. That's basically the probability that it'll go through this barrier. So now, let's try to use the WKB approximation to see what's going on in this middle region that we kind of can't solve very well because there's this pesky v of x that we don't know about. Okay, so normally it would be easy to solve, right? We've done this before, but this time there's this bumpy part that we really can't deal with without the WKB approximation. So let's consider region 2, where in the middle here, so 0 is x. So now here's where we are. And in this tunneling region, we can use WKB approximation. The psi of x has to look like something we know. C over, what did I say earlier? The magnitude of p of x, right? Because now we're in this non-classical region. So because we're in the non-classical region, let's finish our statement here. E to the minus, right, to the minus 1 over h bar. And where are we considering this? We're considering it from 0 to a. 0 to a. And we have, again, this p of x sitting here, but the magnitude of p of x, dx. We'll call it x prime, just because we don't want to mess with if we have an x in here. Let's just not mess with it. Now, this isn't all that we have, right? We have this minus side, but if you remember, there also is a plus side. So we have to write that in as well. Plus, it's a linear combination of the two. This d over square root p of x e to the basically same thing, but plus this time. 1 over h bar 0 to a p of x dx prime. Sorry if I kind of ran out of room there, but I hope you guys kind of understood. It's a copy of this with this sign change because it's a linear combination. So we have these coefficients. We have a, b, c, d, and f. Okay? So how do we solve this? Well, let's consider that we have an exponentially decreasing function here. So that's what I assumed, right? If before we had an exponentially decreasing function here, but I didn't know that it was going to be the same case if we had a bumpy one. But again, we're using WKB, so we're going to assume that's kind of constant. And if it happened for the constant, then it's got to happen here. So if we assume that, we can kind of back out this transmission coefficient, this f over a is approximately equal to e to the minus 1 over h bar 0 to a p x prime dx prime. Okay? So again, we have this kind of similar thing. We're going to say that it looks like that we're going to have a decreasing function here. So now, if we say that, then we know what t is. Okay? So now we know what t is from this little blue ansatz that I said before. We can use that and say that if t is f squared over a squared, we can just square that side. So let's say that t now is equal to f squared over a squared, which is approximately equal to e to the negative 2 gamma. And this is just an easier way to write things. So this gamma is equal to, well, we can define it as actually 1 over h bar 0 to a p of x prime dx prime. Okay, so that's what we're saying this gamma is. So again, we're just rewriting it. We're saying that because we're squaring one side, we have to square the other side. That's what we're doing here. We're squaring this exponential. So we get this t out that looks like this. And if we don't know what v is, we can't really solve that. But that's where we finally get to. Is we get to a transmission coefficient that looks similar to what we've seen before, but different in form. Okay. So now let's take this, and let's do kind of a fun problem, okay? So let's erase all this, and really consider something, let's call it a classical tunneling problem. So this is kind of quantum inherently because we're working with a potential, some potential barriers, but now let's consider this. Let me ask you guys a question. How long would it take for a can of soda to spontaneously fall over? Now, how do we even start this? Well, to begin, right, we're physicists, so what do we have to do? We have to draw a picture. So we have our can here. And a can basically is just a cylinder. So we have, this can has some height. Oh, sorry, I get too used to writing H bar. Some height here. And it has some center point. And if we can kind of draw where it's sitting on the ground is here. And it has some radius, we'll call that big R. And it has some height, and this is half the height, right? Right? If you go halfway up, you gotta get to the center of the mass. So the center of mass is there, it's at h over 2 at r in. So now from this, what would it take this to tip over? Well, in classical mechanics, what do we know? That if this center of mass gets over a point that's not supported on the ground, that's when it'll tip over. So let's kind of zoom into what happens when it tips over. Oh, pardon. Okay, so it's tipping over, and we have this. That's where it's touching the ground now, and if we kind of keep it there, it'll be balanced, right? The center of mass is right over the point where it's touching the ground, so it shouldn't do anything that we don't expect. It should just balance there. So let's call that the y equilibrium. That's kind of like the height that we're at here, at equilibrium. We can say that that's the square root r squared plus h over 2 squared, right? Because we have this r squared, this h over 2. That's how high our center of mass is off the ground if we're just at the equilibrium point, okay? Now we know what's going to make this fall over, probably gravity. So let's write that down. Our potential, depending on y, is going to be equal to mgy. Okay? So now let's kind of work out this tunneling that we were considering before. So we want to know what the transmission coefficient is. So in order to get this transmission coefficient that we were talking about earlier, what do we have to find? We have to find, well, it's not proportional, pardon, that's incorrect, but we have to find it's directly related to this gamma that we were talking about earlier, okay? So that gamma is what we have to find. We'll call that the tunneling exponent. Right, because it's what's in the exponential that might give us some relationship to the transmission coefficient. So let's just turn this mathematical gear here that we're much familiar with now. Gamma is equal to what? It's equal to 1 over h bar times Now, what's our bounds of integration? Well, our bounds of integration, we're going to call that, we're going to say y naught. Let me erase this so I can write something down here. We're going to say up here that y initial equals h bar over, h over 2, right? That's our initial height. Now our y naught, we're going to say that that is equal to y equilibrium minus y initial. So all we're saying there is that's our change in height. So that's like from where we started to where we ended. So now we're going to say that we go from 0 to this y naught that we considered earlier, that we just defined here. And now, what do we have in here? We have p of x. Well, what's p of x? If you guys remember, p of x looks like this. Oh, pardon. E minus v of x. Or actually, right, we're in the tunneling case. So actually, that's wrong entirely, right? That is actually going to be v minus e. Because we're in tunneling mode now. So now we're in that non-classical region that I was referring to. So if we use this p, let's just plug that in to our equation here, where it needs to be. Square root of 2m v minus e dy. Right, because we're considering y here because that's what our potential is dependent on. And then we can turn this mathematical gear, and after I plug everything in, we get square root 2mg n squared, right? Because we could have m from here and m in here, over h bar, because that's where we got the h bar from, and we again have this integration, the square root of y. Okay, do you see where I got that from now? So I'm taking this and I'm just plugging in what we know for v, and that's kind of where I'm at now. So what do we from here? Well, how do we this is easy to solve, right? So let's solve it out, and we get something that looks like this, equal to square root 2, oh, pardon, let me write that again. Square root of 2m squared g over h bar times 2/3 y naught to the 3 over 2, right? Because that's our bound. That came from our bounds of integration, right? From 0 to y naught. Okay. Now, keeping all this in mind, let's kind of keep turning this mathematical gear and solve this out. We have got a bunch of 2's here that might be able to cancel. This 3 might be able to wiggle its way in there somehow. To get a final answer that kind of looks like this. 2m, right, because we can pull out that m. 2m over 3h bar times the square root of 2g all times as well, y naught to the 3 over 2. Okay, so we finally got to an answer where that kind of might be the final solution, but we can kind of, I'll do this math for you because from here it's just all algebra, right? So from here, all we have to do is plug in what is y naught. We have equations for that. So let's just plug in y naught, but I'll give you the mathematical constants that I used when I did this. I used h, oh sorry, pardon, not h bar. H bar we all know. H is equal to 10 centimeters. That's approximately, just I assume that was about the height of it. We can say that R is equal to 3 centimeters. And I like to keep everything in kind of the similar units. And our mass is equal to 300 milligrams. Or sorry, 300 grams. And of course, G, right? G is 9.8. meters per second. Okay? So, what does this give us? If I can erase this equation here, this equation that if we plug in those constants, it gives, I erased our potential there, but we should all remember the potential. It should give us gamma being equal to approximately 6.4 times 10 to the 30. Well, how does that answer a question, right? So what we asked was how long would it take for a can of soda to spontaneously fall over? In this case, we have gamma, but gamma, that's not anything we really care about, right? Actually, we're going to use, we're going to find out what tau is. So, or tau or T, or transmission coefficient. And that is going to be equal to V thermal over, so that's what we're depending on, right? That is what it's probably going to wiggle about. It's probably going to depend on its wiggling from thermal motion, right? It's the thermal motion of it times this e to the 2 gamma that we calculated. And this, if you work it out, approximately equals e to the 10 to the 31 years. So, how long would it take for a can of soda to spontaneously fall over? It would take about e to the 10 to the 31 years, so it's probably never going to happen, which it kind of also makes us comfortable with the fact that our WKB approximation might work out, right? If it works that we see that this number is extremely large, that makes sense because it probably is never going to happen in your lifetime or anyone's lifetime. So that must mean that this is a stable system. And in fact, we know that it is because cans just don't fall over, right?